This is the second video on the Oscillations and Waves multiple choice series. So there's another 10 questions. So what I shall do in a second is show each question, then show the mark scheme, and then I will give a full walkthrough explanation on each question. So if you got a question right but think I could do a bit more, thorough understanding, just watch the questions. And if you got it wrong, obviously I'd advise you to watch the question as well. If you got it right and you fully understand what you're doing, you can skip that explanation for that particular one. So I'm going to leave each one on for a few seconds, so just pause after each question, and then I'll put the solutions on. All right, thanks. So that's all the questions done, and now I'll put the mark scheme on so you can check you're working. So here we go. So give yourself a score out of 10, and then I'll do walkthrough solutions starting now. So number 11 can be confusing because we're talking about path difference. But once you've seen an example, it should be pretty straightforward. What we need is the wavelength of the wave. So we're going to use V equals f lambda. So wave speed is frequency times wavelength. And wavelength is the wave speed divided by the frequency. So the wave speed is 30 meters per second divided by a frequency of 50 hertz. So that gives a wavelength of 3/5, which is 0.6 meters. Then what we need to do is just to look at each path and then figure out how many wavelengths there are in each path. And then rather than use distances to describe the distance, actual numbers, we're going to do it in terms of wavelengths instead. So there's two routes, P to Q, PQ to R, and then straight from P to R. So let's do P to R first. So it's 30 meters of distance and the wavelength is 0.6. So it will be 30 meters divided by 0.6. And that will tell us how many waves are in that length. And it's 50 wavelengths. So we've got 50 wavelengths on that route. And then the other route, which is P to Q and then Q to R, is 38 meters. So we need to do 38 divided by 0.6. 38 meters divided by 0.6, and see how many wavelengths that is. And it's 63 1/3 wavelengths. So 63.3 recurring wavelengths. So the path difference will just be the difference between these two. So 63 1/3 minus 50 gives us 13.3 wavelengths. So that's the path difference, C. Now let's move on to the next one. It's a bit of a classic one. So it's just d sine theta equals n lambda. So I'm going to write that at the top. D sine theta equals n lambda. So that's the equation that describes what's happening with the diffraction grating. So we have 500 lines per millimeter. So we're going to use that to find D, which is the distance between two individual lines. Then we've got the angle 60 degrees, and it's the third order spectral line. So let's find D first. So this is 500 lines per millimeter. So what we need to do is a millimeter, and a millimeter is times 10 to the minus 3 meters divided by 500 lines per millimeter. So if we calculate that, that gives us a distance D of 2 times 10 to the minus 6 meters. So now we can use the equation. So we're going to use d sine theta equals n lambda. So let's rearrange to get wavelength. So wavelength would be d sine theta over n. Then we just need to put our numbers in. So d is 2 times 10 to the minus 6 multiplied by sine 60 divided by, I'm going to try to be neat. There we go. Divided by n, and n is 3. So if you calculate that, we get 5.7, 5.77, so 5.78 or 5.8 times 10 to the minus 7 meters. And if you press engineer on your calculator, put it to an engineering prefix, it'll actually give you 577 times 10 to the minus 9, which is 577 nanometers. The engineering button on the calculator is the ENG button, ENG in capital letters, and it'll be above, you've probably got a Casio or similar type calculator. It's normally above the number 8. So if you're not sure how to use that, but if you press engineering, it'll put it into an engineering prefix, and in this case 577 nanometers, which obviously rounds to 580. So hopefully that's helped. Let's look at the next one. So number 13. So which statement is correct about the properties of an unpolarized electromagnetic wave as it passes through the polarizer? The wave remains unchanged. Well, a Polaroid is essentially you can think of it as a chain of organic molecules. And basically, when unpolarized light comes through, unpolarized light's oscillating in all directions, remember. It kind of puts it into one plane, so it gets rid of a lot of the, the directions in which it can oscillate. So the wave remains unchanged is obviously very incorrect. It's definitely not that. The wave does not pass through the polarizer. Well, it would. The only time it wouldn't pass through a polarizer is if you've got them crossed. So if you have a first Polaroid or polarizer and then go for a second polarizer that's at 90 degrees to the original, then it wouldn't pass through. But in the case of one, it would. The wave's electric field oscillates along the direction of travel. No. D, the intensity of the wave is reduced. Yeah. If you put unpolarized light, for example, through a Polaroid lens, the intensity of the light is reduced greatly. I've read before up to 50% reduction in intensity. So D is the answer. So let's have a look at the next one. Yeah, it's a fantastic question, this. So normally you might look at this and think, so you've got a uniform wire fixed at both ends, plugged in the middle, vibrates at the first harmonic as shown. What is the phase difference? So you might look at this and go, right, P and Q, they're about probably a quarter of a wavelength away from each side. So you might say, they are half a wavelength away from each other. Half a wavelength, lambda over 2, would be pi radians. Which actually isn't an answer, so you shouldn't even fall for that. But it might confuse you, because you'd be thinking, well, there must be a phase difference. But there isn't, because this is actually, it's a standing wave. And in a standing wave, if you are between two nodes, which we are between two nodes, P and Q are fixed between, there's a node there and a node there. So it's on the same half loop. So they're actually in phase all the time, no matter what. So the phase difference between the oscillations between P and Q is 0. If we were looking at a wave, on the opposite side, so say P, I don't know, let's put S there, and it asks for the phase difference between Q and S, they would be completely out of phase. So they'd be pi radians, but because they're on the same half loop, so to speak, P and Q, phase difference is 0. So try and remember that one. So this one, remember when you go from one medium to another, in this instance optically it's of less dense to more dense, the frequency is unchanged. So straight away it's either B or C. If you enter a more dense medium, what happens to your speed? So imagine you are running down a beach, full speed, maybe super fast, coming at 10 meters per second on a beach. You've got concrete ankles that won't snap. So you're running down this beach, and then you hit the water, and all of a sudden you're not running 10 meters per second, you're running 1.5 meters per second, if you're lucky. More dense medium, velocity decreases. The answer is C. Let's move on. Yeah, great question this. The amount of people who students, should I say, that make a silly mistake on this question is, in my opinion, is quite extensive. So this is what is the angle of refraction in the glass. Now, so obviously it's in air, it's going into glass, so when it refracts into glass, it's going to refract towards the normal, maybe something like this. And just for a bit of knowledge, obviously when it leaves the glass and maybe back into the air, well, let's say it goes back into the air, it's going to refract away from the normal as it enters a less dense medium. And in this instance, it'd actually, come out at the same angle that it went in at. So this one would be, well, two of the angles would be the same, which we're going to move on to in a minute. If you did this and got a wrong answer completely, you might be wondering why, because you probably think, well, I did the calculation correctly. It's giving you the 35 degrees, but that's not the angle from the normal. Angles must be measured from the normal. So the angle that you should be using is this one. So to get that, we need to do 90 minus 35, which is 55 degrees. So, and we want the angle of refraction, which would be this one. Okay. So this angle we would get using Snell's law. So that's pretty straightforward. It's m1 sine theta 1 equals n2 sine theta 2. And all we need to do is a bit of funky maths and rearrange to find theta 2. So we do that straight away. We could do, well, sine theta 2 will be m1 sine theta 1 divided by n2, and then just do inverse sine. So theta 2, in fact, I'll tell you what, I'll do it step by step. So sine theta 2 would be equal to n1 sine theta 1 divided by n2. You could do that and then just do inverse sine to finish off. Or we could write it properly. So it's inverse sine n1 sine theta 1 divided by n2. So n1, which is air, now this is the one that you should remember. The refractive index of air, it's I think it's like 1.00729 or something, but we just approximate it to 1. It's basically the same values as in a vacuum. So n1 is 1 times sine theta 1, so that'd be sine 55. If you use 35, this is probably where you made your mistake. And then we're going to divide that by n2. N2 is the refractive index of glass, so that's 1.5. Then you just need to put it into your calculator. And that will give you 33 degrees, or 33.1. If you've actually done all that correct and it's still wrong, your calculator is probably not in degree mode, it might be in radian mode, so please make sure it's in the correct mode. Let's move on then. Now the wording on this one's a bit strange, so let's see what we've got. So we've got wavelength, we've got 400 lines per millimetre, so we've done a few of these now. So we should know that we need to find the distance d. And this is what is the angle of separation between the two second order maxima. So to my understanding, what will be happening is you'll have a diffraction grating. You've got the n equals 0 line. And then either side of that you get, so that might be n equals 1, n equals 2. And then on the same, not the same, on the opposite side, you get the same, a reflection of what's happening. So I imagine we find that angle for n equals 2, and then just double it, because that will be the angle of separation between the two second order maxima. So this big angle. Alright, so I'm just going to get rid of this. Hopefully that's helped. So we basically need to find theta. So d sine theta equals n lambda. First of all, let's find d. So the distance d between two individual lines would be, well, it's lines per millimetre, so it's a millimetre divided by 400. So a millimetre is 1 times 10 to the minus 3 divided by 400, and that'll give us the distance between two individual lines in metres. So that's 2.5 micrometres, or 2.5 times 10 to the minus 6. Then let's just rearrange to get theta. So theta would be inverse sine n lambda over d. Then let's just put our numbers in. So inverse sine. N is 2, so look at second order. Times the wavelength, so 2 times 500 nanometers, so it's just 500 times 10 to the minus 9. Divided by the distance d, which we calculated earlier, to be 2.5 times 10 to the minus 6 meters. That'll give us theta. So that is 23.578. Obviously, you would never give an angle to that level of precision, or that many significant figures. However, we've got to times that value by 2 because we're going from the second order to the second order. And if we use that full number, that rounds to 47.156, which is 47.2 degrees. So 47.2 degrees, which correlates with D. Hopefully that one went okay. Let's move to the next one. So number 18, I'd say it's straightforward, but there's scope for, if you're not entirely sure, then I can imagine it being quite difficult. So we've got the speed of the wave, which is 20 centimeters per second, and it wants the period. So time period t can be, if we use t equals 1 over f. So essentially, if we find the frequency, we can find the time period. So to get the frequency, we can use wave speed equation, v equals f lambda. So we've got the wave speed, we just need the wavelength. So if we zoom in a little bit, wavelength, so one full wave. So lock that for a second. So we can go from that point, maybe, one full wave to this point. So that's 1 centimeter, and this is 5 centimeters. So the wavelength is 4 centimeters. So now I've got wave speed and we've got wavelength. So v equals f lambda, we might as well leave it in centimeters. So wave speed is 20 centimeters per second, so 20 equals frequency f times wavelength, 4 centimeters. 5 minus 1 is 4. So the frequency is 20 divided by 4, and 20 divided by 4 is 5 hertz. And then obviously time period from that is 1 over f. So the time period is 1 over f. So it's 1 over 5. And 1 over 5 gives a time period of 0.2 seconds. So that correlates with answer B. Move on to the next one, sorry. So this one's straightforward, or it should be, but only if you know. So which statement is not correct for ultrasound and X-rays? So both can be refracted. Yes, they can both be diffracted, they can both be reflected, but they can't both be polarized. And the reason why is that ultrasound and X-ray are fundamentally very different. X-rays are transverse electromagnetic waves, so the way they move the particle oscillation is perpendicular to the energy propagation, or the direction in which the energy moves. And ultrasound is longitudinal. So the direction, the particles vibrate is the same direction as the energy propagation. Therefore, ultrasound cannot be polarized because you can only polarize transverse waves. So, C. If you're not sure on that, I would advise to get a book and read about that topic area. The differences between things like sound or ultrasound and X-rays, so transverse and longitudinal waves. So let's move on to the last one. So we've done a few of these, but this one's obviously slightly different again. So this time we're finding the number of lines per millimeter on the diffraction grating, so we need to find D. So D sine theta equals n lambda. So D is equal to n lambda over sine theta. So n is the fourth order, so that's 4, times the wavelength, which is 5 times 10 to the minus 7, divided by sine theta. If you're a mathematician, I apologise about putting 2 equal signs on the same row, but you will get over it. if you've got a proper maths teacher who's a full-on maths graduate, you might have shown that video and it might freak them out. Don't give me a thumbs down though. I do apologise. So yeah, if you do that, you get D. So let's see what that is. So D, the value for D, the distance between two individual lines is 4 times 10 to the minus 6 meters. Then we just need to find the number of lines per millimetre. So if we just do a millimetre, which is 1 times 10 to the minus 3, divided by the distance between two individual lines, 4 times 10 to the minus 6, that will give you 250 lines per millimetre, and then minus 1, which is 2.5 times 10 to the 2. So anyway, that's 2 videos now on oscillations and waves, multiple choice practice. Quite a lot of, different content. Hopefully you found that useful. If you did, give me a thumbs up. And if you've got any questions, just pop them in the comments. So thanks for watching, and I will speak to you soon.